All right. Okay. Here's my slide. All right. Thank you. It just reminds me of a story of people with interesting bios. There was a guy who actually worked at one of the funding agencies for our field, and he used to say on his bio that his job was to throw money down a black hole. So what I want to talk about is, I'm talking about gravitational waves, but the beginning of this story, at least as far as the wider world outside scientists was concerned, began like 3 years ago in late 2015, and basically what we did is we made an amazing astronomical discovery, an amazing astronomical observation, which when we announced it in 2016, on February 11th, I think it was, 2016, it was a huge story. It was front page news on all the newspapers. It was the lead story on TV news all over the world. It was a huge story for for whole minutes. And 2 years later, last year, this led to a Nobel Prize in physics. So it was a big result. And what this was an observation of an event in the universe, right? An astronomical observation. And so when we think normally about astronomical observations, we think of these kind of beautiful pictures that come from astronomers. And actually, this you probably can't read this, but this is NASA has a astronomy picture of the day every day, and this is today's astronomy picture of the day. This is the Cave Nebula, apparently, right? So there's these beautiful pictures of the universe, and that's what we're used to thinking of when we look out into the universe is the light and X-rays and gamma rays and all of this kinds of electromagnetic radiation that we get from the universe that tells us about it. But this observation was completely different. It was a completely different observation. It was a sound. Okay, it was basically a sound, and this was the first sound that was recorded from the universe in some sense. And you might think, okay, what kind of amazing sound was this? Right, to have caused such excitement, was this somehow some aliens playing Space Oddity or something? What could it possibly be? So I'm going to play you the sound which caused so much excitement. Here, this is the sound, which you may not be able to hear. Okay, you probably couldn't hear that unless you were in the front, but there wasn't actually anything to hear anyway. It was just a sort of noise, and then somewhere in the middle of that there was a little pump, which sounded like someone bumping a speaker or a glitch in the Wi-Fi. So that was it. That was what caused so much excitement. So what I want to do is I want to explain to you what that sound was, where it came from, how we recorded it, and then maybe you will then see why this was such an exciting sound. So the sound was, it's from gravitational waves, which are described. We always say this when people say, what are gravitational waves? They are ripples in the fabric of space and time, which is a wonderful expression because it doesn't really mean anything, right? I mean, I could just say, eddies in the space-time continuum, right? It doesn't, reverse the polarity of the neutron flow. It doesn't really mean anything, but it sounds pretty good. And and of course, this comes from the whole idea of these ripples in the fabric of space and time come from this theory from Einstein, and because Einstein is famous for being very smart, and his general theory of relativity, which is what describes gravity and describes gravitational waves, is famous for being difficult. And in the 1920s, after the theory was a few years old, one of the few people who did understand the theory, Arthur Eddington, was asked, is it true that there are only 4 people in the world who understand this theory? And he paused for a moment, and they said, "Are you being modest?" He said, "No, I'm trying to think who the 4th person is." And of course, and it's now 100 years later. Okay, so those guys are all dead. So it's a very difficult theory, but there's many difficult things in the world. And I said this But given that, I will try and explain a little bit about the ideas behind this theory, which I think, which are weird, but not actually. Okay, it's not that they're difficult; it's just they're weird. And okay. So the idea behind Einstein's theory of gravity is that gravity is expressed as curvature of space and time, which again doesn't sound like it means anything. But the idea is that it's actually the geometry of space and time that is being changed by gravity. And you might think that that, again, doesn't mean much. How does geometry change, right? Geometry is just all these rules about when lines are straight and when, you know, angles and things. How can it change? But his claim was that it does change, and that's what predicts gravity. So if you have two, so as an example here, I've got two dots, which you have to imagine represent two, I don't know, planets or stars, some things in the universe. And if you can imagine that they are some distance apart, here's a little ruler, and I've marked these as astronomical units. So these are 10 astronomical units, 10 times the distance. I think an astronomical unit is the distance from the Earth to the Sun. I didn't used to be. Before 3 years ago, I wasn't actually classed as an astronomer. But okay, this is 10 astronomical units apart. Okay, that's what they are. But what Einstein says is that if you put in the middle a huge mass, right, like another massive star or a black hole or something ridiculously massive, well, any mass will do, but it's more effective if it's more noticeable, it's really something really massive, then this will stretch space. And so what will happen is that your ruler will now look like this. And so it will be stretched, and so the distance might now, instead of being 10 of these astronomical units, will be 15, and the space will be bunched up in the middle because this mass will stretch space. And that's what Einstein said that mass does, and he said that's what gravity is. It's a stretching of space and a stretching of time. Right? So clocks will also run slower in the vicinity of this massive object. Okay, and that's what Einstein said, and he did based on this idea. He then, you know, followed it through with lots of calculations, and he came up with his theory of gravity. And you might say, well, that's completely nuts. That's a crazy idea. Only a crackpot would suggest that. And I would agree with you, and everyone would agree with you, except for one thing, which is that every single thing that's been predicted by Einstein's theory has turned out to be correct. So it is a completely nutty idea that space and time are stretched by matter. But if you assume that, it was all true. So yeah, if you assume that that's how things work, then you can actually do calculations that predict how objects move in the universe and how gravity works. And so we're sort of stuck with it. Okay, and that's the thing. So it's not that I think that it's so much difficult to understand this. I mean, I made this really crude picture here. It's fine. The thing is just to accept it, to believe it, and you have to do all these sort of experiments and things to see it's true, and then it turns out it is. Okay, so what comes from Einstein's theory is this, okay, that space and time are stretched by objects, and so another consequence is that if you have objects that are moving very, very fast, like so I have a movie of two black holes orbiting, this is obviously an artist's representation, then this change in gravity of these things orbiting will cause this stretching and squeezing of space to ripple out from them. Right? These changes in the gravitational field will travel outwards, and since this is a theory from Einstein, they'll travel at the speed of light. Okay? And so Einstein said, okay, changes in the gravitational field will travel at the speed of light, and they'll travel out as waves. And these are, a real physical effect that you could in principle measure, except that they're really, really weak. Right? Gravity is the weakest force that we know of, and gravitational waves are a weak perturbation on top of gravity. So they're ridiculously weak, but nonetheless that's the prediction. So if you want to, and so he didn't think you could detect them, he didn't think that would be of any use. But in around the 1960s, people got excited about the idea of actually trying to detect these things and trying to come up with some principle of a way that you could detect them. And so what they came up with was this idea of a interferometer. So what a gravitational wave would do if it passed through this room is it would, as it moved, the room would stretch. And by stretch, I don't mean that all the bricks would be pulled out. I mean that the space would the distance from one wall to another would get larger without anything moving. It's just the geometry would change, and then it would shrink back, and then it would stretch again in the other direction. And so there would be this very characteristic pattern of one direction stretching and the other one shrinking, and then vice versa as they just went back in and out. And so the idea was you could make this thing called an interferometer where you could measure this. So you send these laser beams down two arms, and as a gravitational wave comes through, which is what's supposed to be happening here, you could measure this. And so what happens here is you send out this laser beam, cleverly depicted here. It's split up and goes along two paths, and along each path it goes along, it bounces off a mirror, it comes back, and the whole thing is very carefully set up so that when the two laser beams meet up again, they cancel out, and you get no signal coming out at the screen at the other end. Now then, if the distance is changed very, very slightly, then this interference won't work anymore, and you will get a pattern. And so the idea is that as a gravitational wave comes through, you will get this this dot which sort of appears and disappears on the screen as a result of the gravitational wave passing through. And the idea of using an interferometer is this is something where you can measure very, very small changes, and so it's a precision instrument, because obviously the wavelength of light is sort of hundreds of nanometers, so it's very small distances, so you can measure very small changes. Now that would be great, except of course that the effect from gravitational waves is so weak that a conventional interferometer, and people have been making these things for over 100 years, you could build one in here, you could make a tabletop interferometer, but it would not be sensitive to changes in length as small as what a gravitational wave would cause if it came through from. So the signal that was first detected, this made a change in the lengths of the arms of these detectors that were built that was actually 10 to the minus 18 meters. Now, okay, who knows what 10 to the minus 18 means? I mean, to grasp this doesn't mean. But here is a picture. I imagine no one can prove me wrong. This is a very accurate picture of an atom, and here is an electron buzzing around. And this is 10 to the minus 10 meters, and you can zoom all the way in to a proton at 10 to the minus 16 meters or so, and here's the very edge of the proton, and it moves this little fraction of the size of a proton, and that's what we have to measure in order to measure one of these gravitational waves coming through, right? And you would think this is impossible. I used to think this was impossible. These people building these detectors. I was working on the theory side. It didn't really matter if it worked or not. They were very excited. They were very excited. It was like, whatever. You keep on tinkering away there. It's fine. But it looks kind of insane. But it turns out that you can make something this sensitive. And what happens? So here is a schematic of the interferometer. This is one of the LIGO interferometers, which is the Laser Interferometric Gravitational Wave Observatory. These were funded in the US, so there's two of these things in the US. And they have this setup which looks, okay, it's much like what it was in that animation where there's a laser beam that comes in and there's two arms. The key thing, though, is that to make it work is, first of all, the arms are very long, all right? The arms are 4 kilometers long. Okay, so this is not inside a room. This is out in the countryside. There's these 4 kilometer long arms. And then there's a number of things. There's all sorts of clever tricks with increasing the power of the laser beam, and so on, which I'll go through in a moment, all the different tricks. So here's one of these detectors. This is the end station where the laser beam is, and you can see the arms going out here. This is in Hanford in Washington State in the US. It's there partly because it was cheap land. This was where they used to do, in the Second World War, this is where they tried to refine uranium. So it's probably not the best place to hang out. So it was very cheap to build a detector there. The other one is in Livingston, Louisiana. So it's in the middle of a swamp. And so again, the land was very cheap. Sometimes the alligators are a problem and things, but otherwise it's fine. I think also they had problems at some point of local hunters shooting at the detector, but anyway, they managed to convince them to go, because of course I guess these people all thought it was some kind of government conspiracy to do something evil. But anyway, they were convinced to go away. I'm not sure how, but we won't. We don't have to go into how they were. So there's these two detectors, and they're huge. These huge arms. And what's going on here? There's a third one, there's one in Europe, this is the Virgo detector, which is not far from Pisa. So in terms of locations, it's probably the best. This one came online last year and is not quite as sensitive as the other LIGO detectors, but it's kind of catching up. This is a separate sort of German. It's a French-Italian collaboration. So you can imagine how that works. But it actually runs. Okay. So here are the tunnels, right? There are these tunnels which have the laser beam going along. The tunnels are held at a vacuum. Okay, so the air is sucked out. So these 4 kilometer long tunnels are at one of the most extreme vacuums that's been produced. I mean, I think you could make more extreme vacuums, but usually not through 4 kilometer long tunnels, right? So there's these amazing vacuums to send the laser beams through. I guess there's cooling and all sorts of things. So there's water is often a problem. Also, kind of creatures start to live in there. But yeah, okay. So that's the thing. The mirrors. So the mirrors that reflect the light, the laser beam. These are these huge blocks here that are designed to reflect only to be optimized to reflect the light of at the wavelength of the laser beam of the laser that's used, and then other wavelengths just pass through. So there's these mirrors which actually look mostly transparent, except for the wavelength of the laser light. And then these mirrors are hung. They're hung so that they're isolated from vibrations from the ground, which is going to completely mess up your ability to do this experiment. These things are hung from a pendulum, and the pendulum is actually a fused silica wire, which means actually glass. And then this pendulum, this is not isolated enough. So this pendulum is hung from another pendulum, and then this pendulum is hung from a third pendulum. So you have this triple pendulum system to isolate these, and each pendulum has a different resonant frequency, right? So that you're trying as much as possible to isolate these things from outside vibrations. And then, okay, yeah, sorry. Here's a picture of it. You can see these things hanging here with people working on them. And then, so the laser beam that's sent through. This is actually the laser beam is reflected many times back and forth along the arms before it's sort of released, so that you get many hundreds of times as much laser power, or tens of times as much laser power. And so there's all, and well, actually effectively you get a much longer arm as well. So there's all these things done to make these things more sensitive. You also have, of course, a big powerful laser. One of the things that's going on at the moment to upgrade these detectors and make them more sensitive is actually just to make them work with more powerful lasers. And the problem with more powerful lasers, you might just think, okay, we just spend more money, we just turn up the juice. But the trouble with the laser beam is that then things get hot, right? And so then your mirror gets hot, and when the mirror gets hot, it changes its shape. And all of these things have to be mitigated for, because you don't want any noise sources if you can manage it. Okay, so from the 1970s, when these kinds of detectors were first proposed, until 2015, when they finally saw something, there was construction. Then there was sort of initial run with these things in the early 2000s, and then there was more commissioning to make them more and more sensitive. And so the final product was, I think that this was this curve here. This is the key thing. This is a plot of the level of noise in the detector for different frequencies of signal going through. And you can see that if you can see the numbers here, which you probably can't, this is down to the bottom, 10 to the minus 23, 10 to the minus 22. This is the fraction, relates to the fractional change in length of the arms. So this basically tells you that these things are sensitive enough to measure changes in length of a fraction of the size of a proton. Okay, and one of the reasons that this works, so I used to think, okay, this all sounds, I mean, we all know that atoms are it's all buzzing around, right? There's not these things just sitting there. The reason this works is, of course, not that you're measuring the movement of one proton, you're measuring the average movement of an entire mirror worth of these atoms. And so on average, right, there's whatever, many Avogadro's numbers worth of atoms in there, and on average those can be measured with extreme precision. So this thing, in terms of all the things I'm going to tell you about black holes and all this rubbish, the biggest achievement of these things is the building of this detector and of achieving this noise curve. Right. This is what the Nobel Prize was handed out for, and I think legitimately so. So if you look at these frequencies are actually in the range that are the sensitive frequencies also of the human ear. Right, so these are actually audio frequencies. So in some very real sense, although we're measuring wobbling, ripples in the fabric of space and time, these are wobblings that are happening at audio frequency. So these are like sounds. So this thing is in some sense the most sensitive microphone that human beings have ever built. Okay, so what did this thing see? So this thing was built in 2015. We were going to start doing our first, what I thought was really optimistically called first observing run with this detector. But before that, it was switched on for a week just to make sure everything works. to run all the pipelines and all the analysis codes, make sure everything works. And they turned it on for these tests, and 2 days after they turned it on, in the middle of the engineering run, they got a signal, which looks like this. So you can see here the noise again, and this has changed in frequency a bit so you can hear it more. And what's happening here in time, this thing will stop it. You can see that this is time, and this is the frequency of the signal. So this blip, this blob here is essentially what is a graphical representation of what was going through the detector. And when you clean up the time signal of this noise, you can clean it up pretty easily, and you get this picture of this signal here. So that's the whole signal. That noise that you can hear, that little sort of bump, this is that signal. Okay, and okay, what happens next? So here it is. Here there's 2 detectors, and the reason you have 2 detectors is because these signals are very weak. And I have to say, this first signal, it was amazing, not only that it came so early, we're switching these things on, but also that it was very loud. We didn't expect to actually be able to make a picture of these signals. Right? This was about 3 times stronger than the threshold at which we thought we could observe, pull signals out of the data. So normally you have to use very sophisticated algorithms to find the signals in the data, but this one actually was loud enough that we could make a picture of it. So the problem with having such weak signals is if you see something, you have to convince someone it was real. And if I showed you just one of these plots, you'd say, well, okay, someone bumped it. I mean, it doesn't look very, very convincing, right? So the idea is you have 2 detectors, and you know that there's a time that it takes a light signal to travel between the 2 detectors. And so you know that if you see the same thing in both detectors, with a time difference between those 2 signals that's less than the amount of time it takes light to travel between them, then you can be convinced it's real. And so what's important about this picture is not just that you can see the signal, but you can see the signal from 2 detectors. It says Hanford up there, but there's the Hanford and Livingston detector data have been shifted by, I can't remember the number of milliseconds now, a few milliseconds, and you can see they line up perfectly. So that's what tells you it's really a signal, is that you see exactly the same thing in these 2 detectors. And the chances of seeing exactly the same thing at roughly the same time in these 2 detectors just by some artificial blip is extremely unlikely. We actually estimate this as something that would happen by accident once every 10,000 years, which gives you some confidence it's real. So once you've decided you've seen a signal, you want to know what it is, and this is where, well, in some sense, this is where I come in. So I do my area is modeling the signal that you would expect from black holes colliding, and that's what I've done all of my scientific career. And the way that we do this is we build these computer codes which solve Einstein's equations for 2 black holes as they orbit in and merge and calculate the gravitational wave signal that's given off. The reason we have to do it this way is because you can't solve Einstein's equation on a piece of paper for this kind of system. Right? You can solve Einstein's equation for one black hole that's just sitting there and doing absolutely nothing, and you can also solve them for 2 black holes which are at one moment sitting there. But what you're interested in, of course, is them orbiting around each other like stars, coming in towards each other because gravitational waves are giving off energy and causing them to orbit together, and them merging. And so that's what I work on. We do these simulations. They're extremely computationally expensive. They take months to do one simulation on hundreds of computer cores, and this is sometimes too slow because to actually analyze data like this, you want to consider all possible configurations of black holes, all possible masses of each black hole, all possible ways that they could be spinning and all the different orientations. And so you can't just go around sitting around waiting for months for each of these simulations. So we produce a bunch of them, and then we use these to produce approximate analytic models for what the signal looks like. But anyway, here's the sort of the orbits of 2 black holes coming in from one of our simulations, and here's what the gravitational wave signal looks like from one of them. This is actually from an old simulation I did years ago for 2 black holes of equal mass they're not spinning, they're just 2 ordinary black holes, and they equal mass, and they orbit in over, I don't know whether this is 5 or 6 orbits here, and then they merge. And actually this looks, you might say, very, very similar to the picture previously, and indeed it is. And from these kinds of pictures, we understand that the signal that we saw was from two black holes colliding. And the frequency of the signal and the way that it evolved in frequency, the way the frequency increased, means that it essentially has to be two black holes. So then you want to know how massive, how big were, here's the waveform again, and we want to know how big these black holes are, right? How massive are they? Okay, how fast are they spinning, and so on. So as an illustration of how we do this, here's a picture of a zoom in of my waveform. And it turns out that with these numerical simulations, because of the way Einstein's theory works, you can actually scale these for different masses. So you just take the whole thing and you stretch it or squeeze it, and that's the waveform for a different mass, because it changes the time scale. And if you want to look at how far away the signal is, then you just scale it with strength. So if it's twice as far away, then it's half as strong. So we can take this waveform, and at the moment I've scaled this so it's 200 megaparsecs away, and it's 200 solar masses. So that means the total, each black hole is 100 times the mass of our sun. The total system is 200 times the mass of the sun, and that's this red waveform. This black here is the data that we saw. Okay, so we can just do this thing where we say, okay, let's first push this further and further away, and so that it's at the right strength of the signal we saw, and then once we've got that, about 410 megaparsecs, then we can dial down the mass of the two black holes just to squeeze in the waveform so it looks about the right thing, and then we zoom in and we almost get it right. We sort of overshoot, and then we go back a bit, and then finally we have to introduce the noise in the detector, the noise spectrum, which then rescales it like this, and then we get something that looks almost exactly like the data that we saw, apart from noise. And the total mass of the system is about 65 times the mass of the sun. So these are two black holes. They're each roughly 30 or so times the mass of our sun, and that's what we saw. So essentially that's what we do. We take these waveforms. Okay, I've only looked at two parameters here, which is the distance to the thing and the total mass. There are others, right? The masses could be different, the black holes could be spinning, and so computationally it's a huge, I mean, the people who who wrote the codes that actually search through the data and identify what this thing is, they would be horrified if they saw that all I did was just stretch it and switch, right? I mean, it's like, it's easy, guys, right? I mean, they spend, millions and millions of CPU hours showing what these masses were and getting the error bars and checking everything, and I'm just but anyway, that's the basic idea of what happens. And so in the end, this is what we got: two black holes, 30 times the mass of the sun, right? So they're each, okay, I say it millimeter. They're 30 times the mass of our sun, but since they're black holes, the size of these things is they're about 80 kilometers across. Okay, so you take our sun, you squash it down to make a black hole, you add 30 of them, and you get something that's 80 kilometers across. So when these things entered the sensitivity band of the detector, these things were about 1,000 kilometers apart. They orbited each other roughly 5 times, traveled in over this 1,000 kilometers as they orbited in, and merged, and all of that happened in 0.2 seconds. Okay, so when we say that this is a really violent astrophysical event, right, we're not joking. It's really a big deal. And this incredibly violent event happened, 410 megaparsecs away, which is about 1 billion light years. And so the signal, since it travels at the speed of light, took 1 billion years to get to us. So although it was this violent tsunami of space-time, by the time it got to us, it's just this little, it's like a little wave coming in on the shore, right? And that's what we picked up in the detector. Okay, so that's lovely. We were very excited. Everyone was being called in to be interviewed by TV reporters, and we're all over the front page of newspapers, and there was people got a Nobel Prize. But the great thing here is not just that we saw these two black holes collide, but that this is now a whole other way of observing the universe, right? Because now we have this way of measuring these kinds of sources that we could never see before. No one had ever observed in any kind of way a binary black hole system before, because it gives off no light. This is the only way to see these things. And after that first detection, which was on the 14th of September 2015, we've made a bunch of others. And so, moving it. All right, so here we go. So down the, I'm not sure how many people could see this, but anyway, down the bottom here, there's all the black holes that we knew of before this from X-ray studies and so on, and they're all pretty light, I guess, right? Some of them are only 15 times the mass of our sun, all right? But those are all the black holes we knew about beforehand. I'm not talking about supermassive black holes in the center of galaxies, all of the kind of stellar mass kinds of black holes, okay? And there weren't that many of them. Now, since the beginning of these gravitational wave detectors in 2015, we now have many more of these. So this is the first detection here. There's these two black holes here that formed then a 62 solar mass black hole. This thing actually, when it merged, the energy in gravitational waves that was given off was the equivalent of taking 3 of our suns, 3 solar masses, and converting them to pure energy. Right? So it was 3 suns worth of pure energy that was released in gravitational waves. And if this had been if this amount of energy had been released in light, it would have been the brightest thing in the sky, right? We would have lit up the night. But because it was in gravitational waves, which interact so stupidly weakly with everything, it was impossible to observe without one of these detectors. Okay, so this is the first detection. There was another one a month later, which was a weaker, and we're not quite sure if it was real. Then there was another one that came, actually, it's called the Boxing Day event. It came on Boxing Day, and all of the suckers who were looking at the detector had to work. And then there was a couple more here in 2017. There was actually a final one there, which I didn't mention, which actually came on the June of 2016. It was actually the day on the election day, UK election day. So it was basically the only good thing that happened on the election day was that we saw another black hole merger. Okay, so we've seen a bunch of these things, and you can see there's a whole different population of black holes to what we've seen before. So it's a whole other kind of astrophysical information that we're learning. Okay, and that was already exciting enough. But the other thing, I said, have I completely run out of time, or how am I doing?
You're good. Still another 5-10 minutes.
Oh, wow. Okay. All right. Good. So people aren't going to just walk out then. Good. Okay. So the other thing we saw, okay, that was great. But the funny thing about the black holes is that before we observed anything, what people really thought we would see would be neutron stars merging. Now, I study black holes, so I don't think neutron stars are so exciting, but everyone else does. They're not as compact as black holes. Neutron stars are like, I don't know, about 1.5 times the mass of our sun, and they're compressed down to be 10 kilometers across, okay? Which is pretty dense. It's not as good as a black hole though, but it's pretty dense, okay? And the thing about neutron stars is that people have actually observed them before, because they haven't collapsed to be black holes. They can give off, well, they can pulse. They make pulsars. So if you've heard of pulsars, these are neutron stars spinning, and they have a magnetic field and whatever. Okay, so and people had observed binary systems of neutron stars before, right? So there was this Hulse-Taylor pulsar, which was two neutron stars in orbit, and observations of this over many years were actually one of the first experimental evidence of gravitational waves, because you could see the orbit of these two pulsars slowly decaying as energy was given off through gravitational waves. And Hulse and Taylor got the Nobel Prize in '93, I think, for observing this and basically showing that gravitational waves must exist, because the results of these observations matched up perfectly with the predictions from general relativity. So people knew that binary systems of neutron stars existed in a way they didn't for binary black holes. Right? No one had seen binary black holes before because you couldn't, but they had observed binary neutron stars, and so there was more confidence that these things existed, and people really expected to find these. So there was a general expectation that these are the first things that we would see with these detectors, and all of the analysis codes, right, that were run to basically take the waveform models, like the kinds of things that I produce, and comb through the data and find these signals. A lot of these were set up for neutron stars, because that was what people expected to see. And the other exciting thing about neutron stars that people were hoping to see was that if two neutron stars merge, there was this expectation that they might give off what's known as a gamma ray burst. And what a gamma ray burst is, it's a burst of gamma rays. And gamma ray bursts have been observed for decades, and there's a particular class of them, these sort of short, hard gamma ray bursts, that people didn't know what the source of them was. They theorized that it could be from two neutron stars colliding, but no one knew. And so the big thing everyone was very excited about was observing two neutron stars colliding, and at the same time, traditional astronomers with their X-ray telescopes and their radio telescopes and optical telescopes observing a gamma ray burst, and they could say, okay, you saw a binary neutron star merge, there, and at the same time from that part of the sky we saw a gamma ray burst, and so then case closed. That's the source of gamma ray burst, and that's what everyone was very excited about. And I was kind of secretly very happy that instead they saw black holes, and they kept seeing black holes for a couple of years, and then on August of 2017, I was actually having a rant to the lucky graduate students at Cardiff, all about how all these suckers looking for neutron stars, they're never going to find anything. They should call this a black hole detector. It's just going. And then, like 20 minutes later, everything went mad because they just spotted two neutron stars colliding. And so here is a movie of so in terms of gravitational waves, here's a movie of these are the previous signals that we saw. This is the first detection I talked about, and the other ones. And this is the signal from two neutron stars. So you can see the other one. The first detection was 0.2 seconds long. The next biggest one was this Boxing Day event, which was almost a second. And then here is the binary neutron star signal. So neutron stars are much less massive than these black holes, right? They reach about 1.5 times the mass of the sun, or the same as the mass of the sun. And since they're lower mass, they orbit. They enter the frequency band of a detector much earlier in their in-spiral, and so we get thousands of orbits that we could actually observe before they merge. So this signal actually lasts I think about 60 or so seconds of signal in band. And so it's this incredibly long signal. So it's an amazing thing. And even I, and that's you hear that little whoop. That's the very last bit of it. So it was actually playing the sound all the way. At the end, you can hear just a whoop. So this is an incredible signal. So even as a black hole person, this is just amazing, right? This thing. And the other amazing thing was, as you may have heard, that also it had an electromagnetic counterpart. And it turned out that it was such an incredibly close signal. This was another amazing piece of luck. This binary neutron star signal was stronger than the signal from the first two black holes we saw, and it was actually 10 times closer. Because in general, binary neutron star signals will be weaker, but this one happened to be 10 times closer than the first binary black hole system we saw, and so it made a really strong signal. And then there was all of this X-ray, gamma ray, radio observations that were going on for hours and days and weeks afterwards to understand the properties of the electromagnetic counterpart. And essentially that afternoon, the same afternoon where I was mocking these people who look for neutron stars, we got our proof that neutron stars colliding do actually produce gamma ray bursts. So this was an amazing observation. So that's somehow where we stand now. That was some of the pinnacle of the whole thing, and some what this is described by a lot of people as the beginning of multi-messenger astronomy, a new kind of astronomy where you observe the universe in gravitational waves and in electromagnetic waves with traditional telescopes, and you combine these to get new information. Okay, so that's what's happening so far. What's happening in the future? Well, right now the detectors they've been off this whole year. So it's not like there are any secret observations we haven't told you about. The detectors have just been off, and they've been upgraded, and they're going to be switching on again early 2019. I think February or so is when people are talking about, and they're expected to be about 50% more sensitive. And this means you can see 50% further out. And the great thing about that is because you're seeing further out over a whole volume of the universe, then you have to cube this number to get the amount of the universe you can see. And so we're going to get roughly 3 times as many signals as we were getting previously, a 3 times higher rate of signals. And so the chances also of a stronger signal are much better. Around in the following year or the year after, okay, the detectors will be switched off again. They'll be upgraded further to what's called their design sensitivity, which is the goal sensitivity that we've been planning for all along. And when this happens, the detector will be sensitive enough. We'll be getting daily signals. Okay, so we'll be seeing black hole mergers essentially every day. Now, I don't know how we're going to handle that because it takes us like 3 months to write a paper about every single thing we see. But that's what's going to happen. And so now when you think of neutron stars, people have been observing neutron stars, pulsars, for the last 30 years or so, there's about 60 neutron stars that we know. We've measured like their mass and other properties of them. By 2021, we'll have observed hundreds of black holes this way. So we've got this entire other kind of astrophysical information that people will be able to use. And from this, we will learn about, right, we'll learn what black holes there are out there, what their masses are, how fast they spin, what kind of configurations they're in, and that's going to tell us how they formed, which is going to tell us how stars evolve, what kinds of stars there are out there in the universe, about how galaxies evolve, how the early universe evolved in order to produce all these things. So it's going to tell us a huge amount of astrophysics. It's also going to tell us cosmology. One of the amazing things with this neutron star observation, again, you won't be able to see this, but there's this measurement of the Hubble constant, right, this prediction of how fast the universe expands. And at the moment, there are two different measurements of this which disagree with each other. What is technically said is they're in tension. We don't say they disagree, they're in tension. And now we have a measurement of the Hubble constant from gravitational waves. It's a completely independent measurement, and you may not be able to see it here, but there's a value here which is one measurement, and a value that's the other measurement. And then there's a gravitational wave measurement, which is there's this big curve here, and so this is the range of possible values. It's like a probability density. So there's a big wide swath here, which is the possible values from gravitational waves. So we haven't cleared up what the true value is, but as more observations come and the detectors become more sensitive, we'll be able to nail this down. We'll also be able to understand more about what's going on inside neutron stars, which, apart from just exciting the neutron star people, will also tell us about nuclear physics at densities that we just can't probe in laboratories. Right? So it'll tell us a lot more about fundamental physics at a nuclear level, not just general relativity. And beyond that, so that's the next 5 years or so, beyond that, so there are plans for even more sensitive detectors. There's a detector called Einstein telescope, which is the hope that it will be, different countries in Europe are currently squabbling over who's going to get to build this thing. This will be built underground. It will be a triangular detector where the arms will be 10 kilometers long, and they'll be underground so that they can be even more isolated from vibrations. They'll also be cryogenically cooled, which will help. And so these will be this will be about 10 times more sensitive than the current LIGO detectors. And beyond that, there are plans to put a detector in space. And so to have these 3 spacecraft which follow along behind the Earth's orbit, they will have essentially arm lengths, right, between the laser being sent between these 3 spacecraft, which are millions of kilometers long. And so these things, and of course there's no ground vibrations in space, so these things will be sensitive down to very, very low frequencies, and they'll be able to detect very sort of stellar mass black holes orbiting into supermassive black holes, which will give us incredibly sensitive probes of general relativity, which is great because for 100 years Einstein has been right. General relativity has passed every test, but at some point we'll trip him up. And a detector that's sensitive is maybe the way to do it. The other cool thing about this is this may actually be able to detect gravitational waves from the early universe, and since gravitational waves interact so weakly with everything, we can actually measure gravitational waves or find gravitational waves from earlier in the universe than any other signals that we can see. So this allows us to probe further back into the universe than anything else. And so that's really the future of gravitational waves. And these things will be coming online in the 2030s. So, you know, if you have children who think they might want to get into this field, there's still things to do, and there's a big future. So, thank you.